This summer, I went to Los Alamos National Laboratory with a data acquisition system developed at Michigan to use the Kainu fast array and a Californium fission chamber. There I worked with my mentor, Bob Haight, and in addition, I worked with Patrick Toulouse, who developed the CGMF event-by-event fission model. Additionally, some of our collaborators are Ramona Vogt, Jorgen Randrup, who developed Freya, and Enrico Padovani, who helped develop MCNPX Polimi. The motivation for this work is to provide a simulation tool for nuclear nonproliferation and safeguards for fission applications, so we can optimize, design, and characterize detection systems with simulations. Specifically, these simulation tools lack correlated neutron and gamma ray emission properties, and we hope to help provide a data set for fission models that do capture these correlated properties. Some key parameters that we like to look at and keep in mind for our measurements and our comparisons are detected multiplicity, which is tied with emitted multiplicity, the energy spectra of the particles, and the relative angle of emission of these particles. In the nuclear fission process, a large nucleus that's neutron-rich and unstable splits into two fragments and typically follows a two-peak distribution in fragment mass. These fragments emit neutrons, and in their center of mass frame or in the fragment frame, they emit neutrons isotropically, which in the lab frame exhibits an anisotropic neutron distribution shown in the middle. After neutron emission, gamma rays are emitted, and it is at this point where these correlations arise. In trying to model these fissions, currently, or up to this point, most popular Monte Carlo codes look at average quantities. MCNPX has neutron multiplicity sampling, followed by neutron energy sampling from a single Watt distribution. And the neutrons are isotropic from that model. MCNPX Polimi is slightly more complex. It again samples neutron multiplicity from a full distribution. However, that multiplicity determines the energy spectra from which the neutron energy is sampled. And in the Polimi model, neutrons are emitted anisotropically. The more complex event-by-event fission models, which we are trying to verify and provide a data set for comparison, are CGMF and Freya. CGMF is developed at Los Alamos and Freya at Livermore. And they exhibit these correlations. An example of these correlations, again, is the neutron anisotropy, neutron multiplicity competition with neutron energy, and neutron multiplicity competition with total gamma ray energy emission. So these codes attempt to follow fission in a more physics-based way than current models have. They do not look at averages necessarily, and active collaboration is underway to verify these models with Polimi and with measured data sets. As you can see in the figures, these different codes have very different multiplicity distributions and neutron energy distributions, so that will have to be addressed. To link the measured data sets with simulated data sets, we really need to understand detector response as well. In these measurements, we use the EGA 309 organic liquid scintillator, which is primarily sensitive to neutrons and gamma rays, and neutrons by scatters on protons, and gamma ray scatters on electrons via Compton scattering. One key thing that we have to look at are the neutron light output distributions for neutron scatters on protons, and this allows us to accurately simulate the detector response. Shown here is a simulation result of the neutron efficiency for various neutron energies. Again, these detectors are sensitive to both neutrons and gamma rays and allow for pulse shape discrimination. So neutron pulses have larger tail integrals relative to gamma ray tail integrals of similar total integral. In the fall of 2014, a measurement was performed at Michigan using an inorganic and liquid organic scintillator array. You can see the detectors are 1/2 meter from a central axis, where we measured a californium-252 source. This array provided some of the key parameters that we are looking at. So detected multiplicity, energy spectra, and shown here are the cross-correlation distributions, the measured and simulated. They compare very well. Second-order coincidences agree very well in this case. And the time cross-correlation distribution is simply a histogram of the difference of particle arrival times, both neutron and photon. In a subsequent measurement done at Los Alamos National Lab, where I took a data acquisition system there and used their 54 detector array of liquid organic scintillators, we measured a californium-252 fission chamber source. In this array, the detectors were 1 meter away from the source, allowing for a larger source detector distance, which resulted in better energy resolution via neutron time of flight spectroscopy. By using a fission chamber, we had better timing resolution there as well, and we had greater certainty in correlating our neutrons and gamma rays with a true fission event. And just by having more detectors, we resulted in a larger solid angle coverage, increasing our sensitivity to multiplicity. So this experiment had many channels, and we saved full waveforms. We had 3,000 counts per second per detector of full waveforms, which resulted in approximately 125 megabytes per second of data being saved. And at the end of the measurement, we had 13 terabytes of waveforms. So at that point, that is a very significant amount of data, and post-processing time is significant, and even physical storage space becomes a challenge to back up that much data reliably. So we're looking into advancing onboard calculations and advanced event rejection to minimize the amount of data that we do have to save to shorten post-processing time. To date, only a small fraction of this data has been analyzed. We've looked at double coincidences, but ultimately higher order coincidences are the target measurable. So here you can see off to the left another time cross-correlation distribution of pairs of EJ309s, and on the right we see a key correlation in which the number of neutron-neutron coincidences vary as a function of the detector angle, which is exhibiting the neutron anisotropy from fission. And we will eventually be constructing a detailed MCNPX model of this measurement and the detector response for comparison of these fission models with measured data. So another facet of this work is neutron crosstalk characterization. These detectors are scatter-based, so there's no absorption typically, and they're prone to neutron crosstalk. So a neutron enters one detector, deposits sufficient energy to register as a count, enters another detector, again depositing sufficient energy to register as a count. This adversely creates higher coincidence counts, and we have designed a measurement to address this concern where we shield one detector with a polyethylene shield, forcing all coincidences to arise from crosstalk. And to verify that we have a good understanding of crosstalk, we compared with a MCNPX PLEMI model, and you can see in the top right, this comparison is very good for various detector angles. Key variables in crosstalk include detector, source detector angle, detector to detector distance, and the detector light output threshold. For more details on this, Tony Shin will be presenting a poster this afternoon. And some future work to further carry the investigation into these correlations will occur this winter in a measurement at Lance in the WNR facility. So we will again use the Kainu fast array and a similar acquisition system to measure U-235 induced fissions in a parallel plate avalanche chamber. The spallation neutron source gives us an energy range of inducing neutrons from a few hundred keV to a few hundred MeV. So that will be interesting to look at correlations in induced fission and might have interesting applications for active interrogation. So in summary, we've performed measurements of these correlated parameters from prompt neutrons and gamma rays of californium-252, and this has partially been analyzed. There is a need for a correlated data set to compare these event-by-event fission models with measured data to both verify these models. And accurate models are necessary for advanced safeguards development, and new advanced verification systems could rely on some of these correlations from fission. So I'd like to thank my mentors at LANL, Bob Haight, Matthew Devlin, Patrick Toulouse, my fellowship in NIS, and CVT. Thank you.
So I think of that as yet another sensor. And so what I'm showing here is, here's a scene in which we've taken whammy data, which is video from